In this second video, we're going to be taking a look at Kepler's second law of technically planetary motion, but as I mentioned in the other videos as well, it can actually broadly apply to any object that's orbiting another. So in this case, objects, or planets, originally it was planets sweep out equal areas in equal times. Now I've got ... after that because by itself, it can be kind of hard to understand what that actually predicts. And instead of just planets, this is any object in an orbit. So say satellites, for instance. The big takeaway of Kepler's second law that we get from this sweeping out equal areas in equal times basically boils down to objects move fast when they're in close, and they move slow when they're far out from their central object. So let's switch over to STK. I've got an orbit where I'm looking top down. It's an elliptical orbit, or not elliptical, it's a circular orbit right now, I should say, over the equator. So it's an equatorial orbit was what I was trying to say. I'm going to look down on the North Pole so we can see the orbit dead on. Now, if I press play and I kind of speed this up a little bit, we can see that the satellite is kind of moving at a constant rate the entire time. Now, we'd probably have to get out like a stopwatch or something and make measurements to know that it is actually going at a constant rate. But in short, with a circular orbit, which we get from our first video with an eccentricity of 0, or if you prefer working with the apogee and perigee values, if you have the same apogee and same perigee, you end up with the same distance the entire time. So the satellite is always just as close and always just as far out because it never really gets farther out or closer in. Kepler's second law says that, okay, well, in this case, it'll be going a constant speed the entire time. Now, that's kind of useful. There are plenty of useful applications for circular orbits, but sometimes it can be really useful to try and take advantage of what Kepler's second law actually tells us. But for that, we need to set up, because it's based on, okay, if you're closer in or farther out, so we're going to need a more elliptical orbit. Okay, let's go to a noticeably elliptical orbit. Let's go with something like, I don't know, 0.65. Now I'm going to click apply, but it's going to yell at me because, I don't know why it did that. That's a new one. Okay, well, I expected it to yell at me because we would end up with it being too close in. Let me try moving it out some. Oh, now you think it's going to intersect. Okay, don't know what happened with that other one, but anyway, this is much more what I expected. We're ending up with our elliptical orbit with the Earth at one focus, but unfortunately we're not far enough out, so we're actually clipping the Earth and crashing into it, which is super bad. So let's go noticeably farther out. Let's go 50,000 kilometers. Okay, now we're pretty far out, which is exactly what I was looking for. Now that we have a highly elliptical orbit, we have our perigee here where we're close in, and we have our apogee here where we're far out. Now, because we're noticeably farther out, as we will see in Kepler's third law, when I press play, we're actually going to have to wait quite a while for it to do one complete orbit. But I'm going to bump up the time step. We can see that it's moving real slow out here. Keep watching. And then it's going to speed up. Now it's moving real quick. Slowing back down, going real slow. And then it's going to speed up on the far side, and it starts going super quick. So here's a visualization of Kepler's second law. Now, it's usually phrased in the mathematical way that Kepler put forth that, quote, sweeps out equal areas in equal times. In another video, I could give you more depth on that as to how that relates to the other. But for your purposes, and very useful for satellite orbit design, is taking advantage of one of the outcomes of that. In short, Kepler's second law says when objects are close in, they're moving real fast, and when they're far out, they're going to slow down. And that can be calculated based on the mathematical nature of ellipses, among other things. All right, let's see. Let's go with a smaller orbit than this. I'm going to rewind all the way to the beginning, and let's actually switch this to something that I'm a little more used to, which is apogee radius and not apogee radius, apogee altitude. Dear Lord, that's actually a really large number. Okay, so let's go in and let's say something along the lines of 6,000 kilometers. We're going to put it in a pretty high orbit, and then we're going to bring it down to, I don't know, 400 kilometers at perigee. Now, when I do it this way, instead of relying on the eccentricity and the semi-major axis, I can control things a bit better, and with my perigee being only 400 kilometers, let's just make it 400 even. I know that we're not actually going to crash into the Earth. But we can see that we've got a highly elliptical, or I should say, an elliptical orbit. And let's see, even with us not super far out, let's see what it does. Oh, now it's going super fast, and this is a preview for Kepler's third law because I have the time step a little too high. So let's play it. Now I've gone a little too low. I'm going to speed it up some. So it goes kind of quick there and then slows down. We've got it going much slower here. It begins to speed up. It whips around the planet and then slows back down. So here we've got Kepler's second law of planetary motion once again. And it ties into the first law in that you're not really going to see this effect, at least speeding up and slowing down, unless you have an elliptical orbit. If you have a circular orbit, then it never gets closer or farther away because of how circles work. The last thing I'll bring up is this. I've typed in the apogee and perigee altitude, which is a great way of keeping track of this and staying within your limitations. But now that I've done that, I can switch it over to the semi-major axis and eccentricity. And in those terms, what I've put in has a semi-major axis of 9,578 kilometers and an eccentricity of 0.292. So between 0 and 1. All right, that's Kepler's second law of planetary motion, and a pretty useful one for some of your satellite design. Remember, when the satellite is in close, it moves fast. When it gets farther out, it moves slow.